So now we can look at the radical addition to alkynes. And it happens that these types of reactions are very similar to radical additions to alkenes. So if I start with a terminal alkyne and I react it with HBr, with peroxides, so in the presence of peroxides at minus 70 degrees Celsius, I end up with one of two products. So I either get the Z vinyl bromide or the E vinyl bromide in terms of stereochemistry. Notice in these two products, the bromine always adds at the terminal end of the alkyne, and the hydrogen always adds on the internal carbon. And so you never see the product where the hydrogen is adding on the terminal end of the carbon, right? And if we think about the mechanism of this reaction, the mechanism is going to be very similar to that of alkenes as well, where we have a bromine radical that's generated by the peroxides dissociating to form peroxy radicals and then abstracting a hydrogen from HBr. And so I'm not showing that, but obviously you should know that that is part of the mechanism. And now that I have my bromine radical, that radical can react with a pi electrons. And we can show that right by taking one of the pi electrons, forming a carbon-bromine bond. And so what's going to happen is that bromine is going to go to the terminal carbon, so the carbon on the right, and the carbon on the left is going to become a radical. So the result looks like this. So I have this vinylic radical species. And interestingly enough, that vinylic radical species is actually linear, right? So it kind of resembles an sp hybridized carbon instead of an sp2 hybridized. So that's why I've drawn the R coming off as being a linear in its geometry. So now I take that radical and I react it with HBr. So now the radical is going to abstract a hydrogen from HBr and reform the bromine radical, right? And so, of course, that process is going to repeat and repeat. And if we think about the stereochemistry, that hydrogen can go on the same side as the hydrogen on the adjacent carbon or the bromine on the adjacent carbon. So I'm showing simply one rendition, obviously, right? So this would be the trans vinylic bromide, but you also get the cis vinylic bromide as well. And so if I look at some examples, here I have, let's see, this is 2, 4, so this is one pentine reacting with HBr in the presence of AIBN. AIBN we saw in section 2, right, is a radical initiator, so it initiates the production of alkyl radicals, and then those alkyl radicals can abstract a hydrogen and produce a bromine radical. So we see that either peroxides can be used or other radical initiators can also be used. And so when I react this alkyne with HBr, I get two products, right? Here, so in terms of stereochemistry, I get both the E conformation and the Z conformation of the alkenes. Right? Now, interestingly enough, if I use an excess amount of HBr, right? So I'm treating one pentine with HBr, but now I have at least 2 molar equivalents of HBr, then what happens is I get dibromination. Now, interestingly enough, that dibromination results in the formation of a vicinal dibromide, right? So here I am forming a vicinal dibromide. the reason for this is because upon bromination, that first instance, where you get the products above, there is still a pi bond available that can react with the bromine radical and form its own radical. And that radical is stabilized by the bromine that's already on there, and therefore that's why you get this vicinal dibromide. And we'll talk about this later on. So I just want to remind you of the cationic method of forming dibromides, right? Or the typical addition reaction of alkynes that we've already seen, where you take one pentyne and you react it with an excess amount of HBr, and of course there are no peroxides, so hopefully you have purified your solvents, whatnot. And in this case, the product is a geminal dibromide. So again, we see some regioselectivity that we can use for synthetic purposes.